Nested lists.
A common pattern is to store data, especially numeric data, in a list of lists. This structure is similar to the tables that we saw with nesting data classes and lists, except now every item inside the table must be the exact same type. Structurally, the inner lists all have the same element type, primitive type. The outer list has a somewhat complex element type, a list of primitives. We might also think of this as a grid or two-dimensional list of numbers. The representation is very useful for representing x and y coordinates. Frequently, you will want to loop over the data, just like we did with one-dimensional lists. To do so, we need to nest the for loops as shown. Notice how we can iterate through the outermost list. We get a row for each element. Then we can iterate through each row to get each number. The innermost body of the nested loops represents one individual item. Actually doing something with the individual elements, however, requires state outside of the loops. Much like how our loop patterns had an additional variable outside the loop, we require additional variables outside of both of the loops, depending on what we are trying to do. In the code shown here, we are adding up all the numbers in the list, first by iterating through a row and summing their values, while adding together all of those nested sums. Technically, in this case, we could have added directly to the total variable, but we will soon see another example where we must have inner accumulation variables. In this function double table, we are implementing the nested map pattern by iterating through the list of integers given. For each row, we have to create a new row. We also need to append each new row to a new list in each of the outermost iterations. When we are done, we'll have perfectly recreated the original structure, but this time each of the original numbers will have been doubled. In this last nested loop pattern, we see a modification of the find pattern, where we find the last value greater than 5. We are once again iterating through each, and then through each element within that row. With the if statement inside of the innermost for loop, we ask a question about each individual element. Because we are seeking a property about the entire table, and not just within each row, we can use the same found variable throughout the entire nested iteration. Combining what we have learned about iterating through indexes with what we see now about iterating through two-dimensional lists, we can iterate through the indexes of the grid of data to get access to the x and y positions within the table. Note how we iterate vertically through the table in the outermost loop, meaning that each index represents the y coordinate into the table. The inner loop iterates within a row, so that represents the column or x coordinate. Inside the loops, we have access to each individual x and y coordinate. Instead of iterating by position, we can also access and update specific values within the grid by chaining together the indexing notation. This is actually similar to how we chain together attribute accesses or method calls. Each time we reach another layer of data, we have to unpack the information with another index. The expression grid2 gives a list, so we can unpack that with another indexing by having grid2.1. Much like how we iterated vertically and then horizontally, it's important to remember that the indexing happens with the y-axis first and then the x-axis second. Decomposing complex grid handling functions with a helper function is a smart way to make complicated code easier to read. Instead of trying to do two different loops, we can have one of the helper functions in a separate loop. This example shows how we can turn a list of integers into a single list of integers by mapping a sum function to each row. This same idea can be applied to many other 2D list operations.